Hi, I'm Kyle Hatch. I'm a master's student at Stanford University studying computer science, and I'll be talking about our paper, Contrastive Example-Based Control. Reinforcement learning is a powerful tool that has the potential to help solve many important real-world problems. However, in many domains, including robotics, the practicality of using RL methods is limited by the fact that interacting with the environment to gather data is often prohibitively expensive. Additionally, manually specifying reward functions in real-world settings can be impractical since we don't have access to the ground truth state of the environment like we do in a simulated setting. In order to address these challenges, we follow the pattern of prior work and formulate RL as an offline example-based control problem. In this setting, the agent receives two sources of input during training: an offline dataset without reward labels and a small set of user-provided success examples. These success examples are simply observations of the desired task in its completed state. The RL agent learns to distinguish between the success observations and the observations from the offline dataset, and then learns a policy to reach states that have observations similar to those provided in the set of user-provided success examples, thus learning to complete a task without needing any reward labels or online interactions with the environment. Note that the example-based control setting is similar to the goal condition setting, except that it provides the agent with a bit more flexibility, as the set of user-provided success observations can provide examples of multiple valid ways to solve a desired task. For example, there could be multiple good ways of, say, baking a cake, and the agent would just need to use the set of success examples to learn the way that is easiest for it to bake the cake, not necessarily to learn all possible ways of baking a cake that are represented in the set of success examples. Prior work has approached the example-based control setting by directly learning a reward function from success examples. The probabilities output by this reward network are then used as reward labels with conventional RL methods. This style of approach has been shown to work in both the online and offline RL settings. However, reward learning approaches are often unstable, as temporal difference learning methods with learned rewards can be unstable. Furthermore, training a reward function introduces additional complexity and computational cost, and requires tuning a larger number of hyperparameters. In order to address these limitations, we propose our method, learning to achieve examples offline, or LAEO. Like prior approaches, LAEO learns a policy from success examples in an entirely offline setting, not needing any reward labels. Unlike prior methods, LAEO does not learn an explicit reward function, but instead learns an implicit dynamics model. Once this dynamics model is trained, we can then plug the success examples directly into the model to figure out what actions need to be taken in order to solve the task. At a high level, LAEO consists of two components: an actor and a critic. The critic is a neural network that can be viewed as an implicit dynamics model. It takes as input a state action pair, SA, as well as a candidate future state, SF, and outputs a score estimating the likelihood that SF is an actual future state that is encountered in the same trajectory after taking action A from state S. The dynamics model is trained using contrastive loss, where positive examples are states that are sampled from the same trajectory as the input state action pair, and negative examples are random states. The critic can be viewed as a dynamics model that learns to estimate the discounted state occupancy measure. It can also be viewed as a general Q function that can be used to evaluate a policy for reaching any given state. A policy network is then trained to select actions that maximize the score output by the dynamics model. When training the policy network, the states are sampled from the offline dataset, and the candidate future states are sampled from the set of user-provided success examples. We choose the future states input to the dynamics model to be selected from the set of user-provided success examples so that the policy network is trained to choose actions that will lead to states similar to those in the set of success examples. We also add a behavioral cloning regularization term to the policy network loss in order to prevent acting on out-of-distribution state action pairs. In summary, LAEO is an actor-critic method, so it learns two components: an actor for choosing actions, and a critic that predicts the likelihood of being able to reach a given state. Note that we're using the terms critic and dynamics model interchangeably because the critic is really both a general Q function and an implicit dynamics model, depending on how you view it. The inputs to our algorithm are an offline dataset without reward labels and a small set of user-provided success examples. we trained the critic to be an implicit dynamics model that predicts the likelihood of reaching any given state. Then we trained the actor network to choose actions that will lead to states that are similar to those in the set of user-provided success examples as predicted by the critic. This allows us to train a policy without training a separate reward function or using TD learning. An illustrative example of how our method works can be seen on the simulated image-based block pushing task. On this task, the agent has to push a block to a target location. The agent is given success examples, which are images of the block shown in its target location. On this task, reward learning-based methods such as oral struggle to achieve high success rates. In contrast, LAEO achieves much higher performance. We evaluate the performance of LAEO across 7 similar manipulation tasks and compare it to behavioral cloning and 2 reward learning-based methods, oral and Pearl. Here, the average success rates of LAEO are shown by the blue bars. The top plot shows the success rates of LAEO versus the baseline methods on state-based tasks, and the bottom plot shows the success rates on image-based tasks. We find that LAEO matches or exceeds the performance of the other methods on 6 out of the 7 tasks. Additionally, LAEO is more stable than oral and Pearl, which use learned reward functions with TD learning. We also test the capacity of LAEO to learn in partially observable settings. In this experiment, we change the camera angle on the push block task so that the exact position of the block can't be seen when the robot moves its arm to touch the block. In this setting, the environment is no longer Markovian, greatly increasing the difficulty of solving the task. The highest performing baseline on the fully observable tasks, oral, significantly drops in performance in this setting. While this partially observable task is still more difficult for LAEO than the fully observable version, LAEO does not use TD learning and does not assume that the environment is Markov, and is therefore better equipped to learn in partially observable settings. The highest performing baseline in the fully observable setting, oral, drops to around a 30% success rate in the partially observable version of the task, whereas LAEO is still able to solve the partially observable version of the task over 50% of the time. Additionally, back in the fully observable setting, we perform an ablation over the number of success examples provided during training. We find that LAEO's performance remains virtually constant when using 200, 100, 10, or even 1 success example, whereas reward learning-based methods decrease in performance as the number of success examples decreases. In summary, in comparison to reward learning methods, LAEO does not train a separate reward function, does not use TD learning, requires tuning a fewer number of hyperparameters, and is more stable than reward learning-based methods. LAEO also outperforms reward learning-based methods in partially observable settings, and in settings where a very small number of success examples are provided during training, even maintaining virtually unchanged performance when only 1 success example is provided. We are currently doing some promising ongoing work on training LAEO's critic network on multiple different tasks so that it can learn a general dynamics model that can be used for multiple downstream tasks. Thank you for listening to this presentation, and feel free to contact me with any questions or feedback. Please stop by the poster to talk about our method in more detail.